Okay, well, I'm sure a few more people will file in as we get started, but in any case, so before I give it over to our speakers for this afternoon, I just wanted to announce that this afternoon at 4:30, we're planning to walk over to Jupiter, which is a nearby bar. They also have pizza if you want to order something for dinner, so we can have a bit of a happy hour and, kind of hang out in a bit more informal environment. So if you'd like to join us, just meet by the entryway, the main entrance at 4:30 p.m. Great. Without any further ado, I'll give it to Gil to talk about tree codes.
So hi, everyone. It's really great to see all of you. Thanks for the invitation and also for a really nice workshop. So I'm going to do something slightly different than the other talks. I hope it's okay, but it's going to happen. So instead of talking about a new result, I want to talk about an old problem and things we did around that problem. And my goal is actually to try and invite you. That's why the invitation there, to think about it. And so in this talk, I really want to share my love for this problem and tell you why you need, why you should try and tackle it, okay? So I don't want in the middle of the talk to start side things. So it's going to be I'm going to base this talk on a joint work with many great people. Schulman is the father of tree codes, and Tal, you heard quite a lot until now. Right, so there's that. And so I can start with the definition, but let me be a bit more dramatic and philosophize a bit further. So, you will see this definition of a tree code. You will see it's really elegant and nice and simple and inviting. Like students love to hear about this because they get the problem in a second, and then they think that it's proportional to the time it will take them to solve it. Sorry, Tal, by the way, that I'm telling you this now. So, after the workshop will end and you will be remembered of this talk, you'll say, maybe I should work on tree codes, and you'll try, and it's good. And you will do what everyone, I guess, tried to do initially. So you'll take your toolkit, error correcting codes, and or stuff, underline them, and you'll try to see if it works. And if you think about it, and I don't want to be too reductive, there are only two things we know how to do. There are polar codes, but there are evaluation codes and there are expander graphs. Right, evaluation code goes a long way. There are the vanilla Reed-Solomon, then you have multidimensional like Reed-Muller, derivatives. If you are adventurous, you do AG codes, algebraic geometric codes, and so forth. You can group things, you can do a lot of stuff. But at the end of the day, it's evaluation codes. And tree codes are not impressed by evaluation codes at all, it seems. Their structure is different. And then there is the other thing, which are essentially expander codes, but not really, because there are a lot more than that to that. There are unique neighbor expanders, and there's spectral expansion, like the long-Char lemma, and then there's HDX now, and so forth. And in Irit's talk, you actually saw like a meltdown of these two together, like in a very strong way. But again, it seems that tree codes are not impressed by expander codes as well, at all. So at the best case scenario, you will be able to sit and construct a tree code, and at the worst case scenario, you'll figure out that you'll need a new idea, and you'll introduce a new idea to coding theory. Are there really codes? Are there really codes? You can reduce. But it's codes. Technically, you need to pad it a little bit to be a code, but it's a code. Right. So anyhow, with that, I want to actually start. But I really think that this problem will kind of stretch your understanding regarding techniques we know and love, and hopefully you can stretch it enough to actually do something with that. I'm really pessimistic, and I think you need new ideas. You need a third code. So let's see. Okay. So, but let's start. So what is a tree code? So there's the definition. So what you do, what you're looking at is the infinite binary tree, rooted binary tree. You have this root, Okay, there's one of those, but so what's a tree code, or what's more precisely, what is a delta tree code? Delta is a kind of a relative distance parameter between 0 and 1, hopefully not 0. So that's actually a coloring of the edge set, of the edges of this tree, with hopefully as few colors as possible. So I'm just going to use 2, but we'll see in a second that it actually doesn't work. And despite the fact that you have few colors, so the color set is, let's call it numbers 1 to C. Despite the fact that you have only few colors, in particular finitely many colors, you want this tree to be colorful. So in what sense? So if you will zoom out from this tree, then the property that you want is that for any 2 vertices U and V of equal depth, you want that if you trace back to their least common ancestor, let's call it W, and let's assume it's L apart, L away from U and V and L in edges, never mind. Then you see here you have, if you look at the colors, you have a element in C to the L, and also here, and you want the Hamming distance between them to be at least delta L. Okay, so you want delta fraction of disagreements. Okay. So I don't know. When I saw this thing, I kind of imagined it doesn't exist because there are many tests and like 5 colors or something. It seemed to conflict my Ramsey intuitions. So let's see. So what do you think? Can you construct a tree code with 2 colors? When I say tree code, I don't mean about what delta is as long as it's larger than 0. Okay, any constant larger than 0. 0 is easy. You need 1 color. But for 2 colors, with 2 colors, can you do it? Anyone other than Tal, essentially. Just say no and then no. No. No, good. So the reason you cannot do it is because, well, this is the root. Someone gives you hands over, here is my tree code with 2 colors, and you're impressed. And you say, well, first of all, the first observation is that 2 siblings, like direct siblings, can't have the same color connected to their parents because they will be the reason the distance is 0, right? Because you got 0 out of 1. So it's always the case that when you look at 2 siblings, you get different colors getting to them. And so this means that the only kind of artistic freedom here is whether choosing if you go left or right with the purple or the blue, which doesn't matter at all. And in particular, it means that you can kind of generate an infinite or infinitely many pairs or infinite path like that, where on this path, only the first edge disagree. So the distance is going to be smaller than 1 over L for any L. The infimum is 0. Can you do it with 3 colors? That's actually harder. And don't put it on your exam in discrete mathematics courses, by the way. So also no. And if I would have given you a couple of minutes, you would immediately figure it out. So the reason is that you can look at, okay, here you can't do much, but here you have 4 edges going out. You have 3 colors, good, I don't need more. So think about it, you have 4 colors, 3 edges. Pigeonhole principle tells you 2 of them will be of the same color. If the 2 of the same color are siblings, we are done. So they are not the same siblings. So they are going here and here maybe. But then you can continue, right? Looking at these 4 edges, these are not the colors, just the edges. You can continue on and on like that. Maybe it's not all purple, but it's always a green. Can you do it in 4 colors? That's an unfair question. The answer is you can. You would imagine maybe it's not. That's my was feeling at the beginning because, okay, the second level won't give you that, but the third one might. You can imagine a case-by-case Ramsey type analysis, but it doesn't work. And in fact, there are 4 color tree codes, and the distance is also not so, it's not so bad. I think it's something like that. It's an irrational number or whatever, but it's large. Good. So what's the problem? The problem is trying to construct these tree codes. I mean, we understand them. we understand them I mean, if you look at LCC, for example, which everyone talked about all the time, these are also codes that have structure. It's not like a random thing will work. You need structure there. And tree codes are also like that. You can't just throw in like random coloring here. So these are two problems that require structure. And here we are much happier in the sense that we do understand what's our goal, at least. In LCC, no one knows, right? Log-ends, 2 to the squared log, and so forth. So at least here we know what's the goal, but we don't know how to reach the goal. So the main open problem I want to pose here, it's not me posing it, just delivering it to you, is construct. If you do 5, it's okay. Constant number of colors, tree code with constant distance. That's a problem. We don't know how to do that. It's open for like 30 plus years.
So what we expect is it like polynomial time in the
Yeah.
sense of,
Good. No, good. You need to run in poly aleph fs or something. No. So no. By construct, I mean that given a specific edge, and maybe it's in the depth n, so you need like n bits to describe it. You want in poly n time to report the color back to me. Yes. Right. It's like a strongly explicit construction. That's what we would need. And I should also say that this object, which was introduced by Schulman in '93, came from, the motivation was interactive coding schemes. I don't want to get into that. If you want, you can definitely go and ask Ran Geles and Klim Flamenco here, which know much more than that about me. Like Ran literally wrote the book. But the idea here, let me just say it, we converse with each other, unlike the Alice and Bob something. Imagine a situation where two people are actually conversing, they want to exchange bits, and over a noisy or imperfect channel or adversarially controlled channel, and they want to exchange bit by bit. And instead of doing that, they are going to use the tree code if they had one, the same one. And every time, so maybe Alice is sitting here, she wants to send a 0, I interpret 0 as going left, and instead of sending the 0, I'm sending the color that appears on that edge. And we continue like that. Bob controls the odd levels, Alice controls the even edges, layers. And the point is that maybe at some point we kind of diverged and we didn't talk about the same thing anymore. So I sent you something, but the adversary flipped the color, and this is the time where we didn't agree with each other anymore. We don't know that, but that happened. And after some time, maybe that's me and that's you. And if there are many different colors here, if like one change caused this, snowball to roll, then you can imagine some protocols be able to kind of at least detect that, right? And then you'll try to kind of go back to that place, rewind. Right? So protocols use tree code in a much more sophisticated ways, increasing significant ways. Most of them don't even need tree codes, but that's kind of the motivation for this definition. Any questions?
Yes, you just alluded to the fact that sometimes there are workarounds that we can get applications without using tree codes. So
yes.
Are there any remaining applications that crucially depend on?
So to the best of my knowledge, if you were insisting on staying deterministic, like you want the compiler to produce a deterministic, unless you assume something strong, you have to have a tree code. Right. But Ran maybe can correct me. But for me, I don't really care. So like, look at this. It's like, why can't you construct this? Okay. So what do we know? So maybe I'll write it there. It seems like the podium. So we don't know how to do that. So we relax the problem. And what do we know is to construct tree codes where the number of colors increases just with depth. Okay. So the obvious thing is like using 2 to the n colors at depth n. If you have 2 to the n colors, you can just color every edge in a different color. It's crazy. Poly n number of colors is non-trivial, but it's not a paper. Okay, it's like it's not a homework question also a little bit, but if you want poly n colors, you can do that, and that's actually a note by Schulman, Evans, and so Evans, Klugerman, and Schulman. And then a couple of years ago, we reduced that to poly log n. But this poly was large. I mean, not large, but it was larger than 1, definitely.
It's smaller than 69.
It was actually 2 plus square root of delta. Delta is there. And then a couple of years later, we reduced this to log n to the square root of delta. There is an O here, but never mind. Which in particular means that if you are willing to go with distance which is which makes this constant, namely 1 over log n squared, you get constant number of colors. And before that, there was a 1 over log n distance construction by Hopler, Ran, Cole, Recursion, and I'm missing the one that's here, right? Noga. Yeah, I knew it. Well, there are 2 of you here. That's not fair. Most important, of course, most important. Tie with Victorson. Okay. So good. So out of this also came out of this came one. It turns out that it's even hard to kind of pinpoint a candidate, a plausible candidate for a tree code, because there is a structure. You need to understand the structure. Even if you can't prove it works, you need to understand it. So I want to talk about the conjecture that came from these works, which seems to give you a tree code. And there is another conjecture which I want to talk about by Moore and Schulman, but there is another one. So this is essentially everything we know about tree codes, like 10 papers. Okay. So help. We need your help here. It's really easy to get into this problem because there are not many papers to read. And sorry?
Never get out.
Exactly. That's a rabbit hole. And
maybe another high-level question, like is there a more general problem of which tree codes are a special case? Because there is a certain topology here, and one could think of more general.
That's true. And besides like obvious things like larger rarity and so forth. Yeah, so Leonard has this general question that he likes more, but I don't remember the details. Something about symmetries that you try to break here in a more general form, but I don't remember. Are you alluding for something specific that I can, maybe you'll give me more?
No, I mean, you could imagine all kinds of generalizations of classical operating codes where the sets were, like...
Right, I see.
So I'm wondering if you can cast it as some kind of instance of the more general.
Right. Yeah. Okay, I'll need to think and remember what Leonard has in mind. Okay. So what I want to do is kind of to tell you about this construction and that construction. It uses that one to give you a flavor of what do we need to do when you try to do this. Okay. So, what should you do? You have to choose now. There is a junction. Either you do expanders or you do evaluation codes. That's the 2 things, and there are polar codes. They always destroy the story that I'm trying to say here. So let's try to do evaluation codes. So what's the problem? So imagine someone gives you the message. So what do you mean by message even? So by message, I mean these are the bits, either 0 or 1, you go left or right. Okay? And in fact, it will be, as you all know in coding theory, it will be more convenient to work with a larger alphabet and then worry about concatenation. And in fact, it will be best to work with an infinite alphabet. But don't worry, we are going to use a finite chunk of it, but it's better not to limit yourself at the beginning. So assume that all the message inputs are just numbers. And the output, the color, let me be specified and say that the color output is going to be z times z. So in a sense, it's read half, but depending on the size of the numbers, of course. And the code that we are going to construct now is going to be systematic. So actually, this is the first copy of z that you're going to output, and then you're going to output another bunch of numbers. So let me write z here, and this is the output, z times z, okay? So what should you output? You're given this message. What should you do? What's the best code there is? Read Solomon, exactly, of course. Read Solomon. The rest are copycats. Read Solomon. Okay, so forget about the fact that there are infinitely many messages here. You can do Catanic. Let's kind of look at a particular point now in time. So the thing you may want to do is kind of, consider the polynomial whose coefficients are those, for example, or something of that sort. Encode the message as a polynomial, give it the form of a polynomial, and evaluate, right? That's what you want to do. So let's try to do that. Actually, it will be more convenient to do the other way around. So at time t, I'm not going to tell you what I'm outputting for a second. I'm going to delay it. And at time t, so what you're going to do is you're going to do the usual thing. Essentially, you're going to consider the polynomial. Usually you write f, but now it's z, and then that's going to be q. You're going to look at the polynomial f sub t that interpolates through these points. Okay, so more precisely, I'm looking at the unique degree at most t polynomial such that ft at time I equals mi for all I smaller than t. Right, you can do that. It's kind of the dual way of doing Reed-Solomon. It's slightly more convenient here. And, let's write it more explicitly. So the equality is for there. It's the sum of some ci x to the I go from 0 to t. And what should I output, I guess, given that I wrote ci now? Ct, exactly. But you know that, you should be ashamed. Ct, I'm just kidding. So what's the problem with that? I mean, forget about distance or rate or anything. Like, it's something that doesn't add up here. Same alphabet? Yeah, okay. I'm fine with like having two z's here. But there is not like, there is not back. Right. No, Ct depends only on MT. But there is no backward support, right? The coefficient of ft, the coefficient of x squared in ft, is not the coefficient of x squared in f3, f4, probably up to ft minus 1. The coefficient always change. Very good. But so that's the problem. I mean, it's not a problem. It's what it is. But you imagine you want some stability. You want the same polynomial to be there so you can analyze it. You don't want to change under your feet all the time. So again, so what you'll do is exactly as you said, you're going to use a basis that kind of respects your choice of evaluation points. So you're going to use this basis, x choose I. It's exactly what you think, it's x choose I, it's a polynomial. And it's not hard to see that actually, I mean, in numerical analysis, people use it because it's stable. Like the previous coefficients don't need to get updated all the time. So it's linear time rather than squared, it's stable. But it's not hard to see that now you respect the past, right? So the only thing that will happen, the difference between ft and ft minus 1 is ct. Let me call it gamma I because I'm used to it. The c was just for the failed version, and now it's gammas. So that's the construction. That's the old construction. And let's try to analyze that. So again, so I'm hoping I'm clear. So this determines the edges that you're going through. It's now a ZRE tree, but okay. And and you write both the edge name, like the edge name at time t, both the edge name and this thing. Okay, so when you come to analyze the distance, you have to do distance and rate. When you come to analyze the distance, you will look at the following picture. So, let's do it like that. This is the output. There are pairs. And what will happen is that you'll say, maybe the split was at some point. Let me change it, R for split. Maybe the split was at some point. Like here we disagreed. Here this thing is non-zero. It's a linear code, so you can do the zero, non-zero. Here it's non-zero. And I'm going to go, that's the split, that's the ancestor. As you move along, you get the pairs of u and v that you're looking at. So I'm going to look at this point in time. Maybe it's, let me write it as R plus L, it's L ahead. And what you're outputting are these pairs, right? So you want these pairs to be, you want, say, 1/3 of them to be non-zero pairs. Now, if the gamma i's, if those are non-zero by themselves, many of them are non-zero, you're happy, you won. So the only problem is that many of these gamma i's will be 0. And then you will want to argue that many of these are non-zero. But what does it mean that the gamma i's, many of them are 0 about the polynomial? How do you call a polynomial most of whose coefficients are 0? Sparse, right. That's why R is for split and S is for sparse. We respect the sparseness more than the split. So you're going to have to ask yourself the following question. I'm looking at this polynomial. Let me write it slightly differently. So here I wrote only the non-zero gammas in this notation. So I have a sparsity S polynomial. The CI's are just numbers, where gamma is non-zero. The degree is like CS, right? But the sparsity is S. Could be much smaller. And you have to ask yourself the question, how many zeros does this thing have? I mean, you want it to have not too many zeros. But it has a lot of zeros. It doesn't work that way. I mean, the zeros depend on degree, not on sparsity. For example, x choose d has d zeros. Regard its sparsity 1 polynomial, it has d zeros. And you said, well, I know where the zeros are, it's fine, there are 0 up to d minus 1. Okay, but you can take this thing. So it's a sparsity 2 polynomial. Let me also, slightly decrease the effect of this thing. So that's essentially putting this function on a slightly sloped line like that. So all the zeros move, I don't know if it's upward or downwards. I should think about downwards, like over here. There are many zeros there, and you don't really know where they are, right? And so the question is, what can you do? And the main theorem kind of supporting the analysis of this is that actually you can say something. You can say that this thing has at most S minus 1, sparsity minus 1, non-trivial. Is it okay for zeros in integral zeros? What do you mean by non-trivial? So all of these are 0. All of the summons are 0, before C1. So you don't care about them. They correspond to the zeros from before. They have nothing to do with the code, the distance that you try to analyze. But after C1, from C1 onwards, in integers, there are at most S minus 1 roots. Okay? Not in integers, there are probably CS roots, but it turns out that they tend to be non-integral. Okay? So that's the basis for the distance analysis here. Yes, sorry.
That statement are you using that the gamma i's are, you need them to be integers for this?
No, it works if they are real. Right. Oh, it's actually interesting that you said that. So because I need it for the rate now. So for the rate analysis, if there have a question, it turns out that in the Newton basis, in the standard basis, you will get Q, right? You think Lagrange interpolation, you see quotients. But in the turns out Newton basis is also fun because it gives you a polynomial over the ring rather than over the field. So that's nice because you don't want to analyze rate like in terms of quotients and so forth. That's just cleaner. So what about rate? So that's kind of the slightly sad story. So in terms of rate, you can actually write a formula for gamma t. It's not hard. It's kind of Mobius inversion thingy. And you can show that the gamma t is at most 2 to the t. So that's bad. You don't want to see 2 to the t. It increases exponentially with time. The more you wait, the more you write, right? But time something which makes sense about it. It's kind of the maximum mi. That's fair. Like you blow up things by a factor of 2, it will blow up by a factor of 2. So this tells you actually that you read, let's call this thing m, or maybe let's call this thing 2 to the m. So the mi's are m bits. So you read m bits, that's what you read. And what you write, so it's systematic. You write m bits just for the systematic part, and then you have another m because of that, and another t. So you get 2m plus t bits you write per m bits you read. Right, because the systematic give you an m, and then this is m plus t bits. So this means that it doesn't work for binary. If m is like 0, 1, t will destroy everything. It works best when t is equal to m, for example, or larger. Okay, so this makes rate 1/3, for example, when t equals m. Right, so let me write it like that. And the distance is 1/2, but never mind. But I want binary tree code, so what do? Tricks. Someone said gymnastics in one context, and that's like tree code gymnastics. What you do is you say, okay, you want, you give me n bits, I want to construct a tree code. So what I'm going to do is I'm going to split the n bits to square root of n blocks of square root n bits each. So this is going to be the m, because, okay, that's the symbol for me. And you're going to have t, which is square root of n blocks. And then, if you think of this as one chunk, you can use the tree code to, it takes this symbol and it says output that thing. And you're going to output it, but you're going to output it here, right, afterwards, because you have to be online. The tree code is online in the resolution of chunks, not in the resolution of bits. So you have to wait a little bit to do this. And then you have to, worry about the present. Like square root of n ahead, you're fine, essentially. But now you are not fine. So what do you do in the square root of n thingy? You recurse, right? You do it again and again. And you need to, there are like 4 technicalities that you need to do. You essentially recurse. So you have log n iterations because you recurse square root of n kind of recursion. And each time you have a kind of a rate 1/3. So the overall, and you concatenate all the results. So overall, you have rate, which is, you write, some order of log n bits per bit you read. So that gives you the, 2 to that is the number of colors. So that gives you the polylog n number of colors.
Even if you construct a high rate code, positive rate code over a large alphabet, it's not giving you something.
Right. Yes, it's because the trade-off here, because of the t here, it's the t, not like a log t would be perfect. Because it's a t, you need to worry about the best trade-off is something like that, and then it determines the recursion level or the recursion depth, and when you do log n of those and concat, you don't do something more complicated, maybe there is something better to do, but you just concat all the results. And every kind of tree code is worrying about its own time interval.
Is there a question about large alphabet tree codes that will answer binary tree codes?
So in this specific setting, you want to improve the dependence on t. But maybe it's a completely different kind of dependence on t and so forth. But here you want to get it smaller, and then but it's not. Then you are immediately fine because kind of techniques like that.
I thought maybe Swastik was asking, suppose you have, if your message symbols are over an alphabet of size n, and your colors are over an alphabet of size polynomial in n.
Yeah.
That would imply.
Yeah, that will give you a tree code.
That would give you constants.
But what happened here was that, that n is the same n as the depth of the tree. Is that?
Yes.
So
So that's the things are
here the alphabet size is too big.
Yeah. Which makes you use recursion. If it was like log n, you didn't use recursion, you use like brute force, like small tree code or something. Yeah, exactly. But you definitely want to decrease the dependence on t here, right? That's what you want to do. If it's log t, which essentially corresponds to exactly what you said, then it's fine. How much time do you have?
But in this construction, 2 to the t is the best whole.
Yes. I think 10 minutes, right? Okay, yeah, good. So let me tell you how you reduce this t, but not like log t, just because log t would be in a completely different talk. So, I would be happier to speak. Okay. So there is, again, so we have the toolkit of error correction, and this if you think about it for a while, this almost screams tensoring. Because we use Reed Solomon, I told you Reed Solomon is the best. Actually, it's like, Reed Mueller has this effect of putting square root on stuff like that, right? So the idea is maybe you can do kind of tensoring. So what do I mean? So you start with this construction, you're not giving up on it, and you have n bits, and what you do is you split them to square root of n and square root of n tensor like rectangle like that, square like that, and you apply the tree code on every interval, completely forgetting what happened here when you're operating here. Okay, so that's good because there is a square dependence rather than there is a square root dependence here because you're just going all the way up to square root of n. But now, okay, and now in tensoring, what you usually do is now you take what happened and you operate on the rows with the same tree code. And you can do that, and it actually doesn't give you anything. The better thing to do is to now consider this tree, this thing, you applied the tree code, you got something here. Now you think of this as your alphabet. Because this tree code thrives when the alphabet is large. Like, that's what it does best compared to the length. So you take your input, you apply the tree code, and now the symbol sits here. Technically, they sit one row down all the time. No, it's okay. They sit here. And then you apply a tree code of the same length, square root of n, but actually it has to work less because the alphabet size is larger, because the tree code added something. And turns out that you need like half a dozen tricks to make it work, but that's essentially the idea. And what it does, the effect that it gives you is that it translates this. First of all, you can remove. Okay, so the first observation was that you can make these two essentially a 1. So let's write it as 1. So it takes something that looked like that. No, it takes something that. I'm slightly lying, but it's okay. It takes something that looks like that. So that's this tree code with a 1 instead of a 2, which is a slight lie, but that's okay. Don't worry about that. And it makes it has a slightly worse dependence in terms of m. I mean, when you do it, you get something like that. So you add something multiplied by m, but t becomes the square root of t. You're happy, right? Because once that happened, you can recurse. And you recurse, essentially log n times, if n is your last t. And so it will give you something like a 1. The 1 is just to make sure you're not compressing. So let's ignore the 1. So it's a square root of delta times log n times m, and this kind of vanishes. And from here you can see, now it looks like a standard rate thing. You read m things, and you write this number times m things, so this must be the rate. 2 to the power of that is exactly what was written before, log n to the square root of delta. So this is how we get the log n to the square root of delta. Just tensoring, essentially, but essentially. Okay, and now in the last 3 minutes, I want to say the conjecture that we have. It's a funny conjecture because even if it's wrong, you can't disprove it. It's like a good science. You'll see. So, but it's right. We checked. It's okay. It's fine. So if you think about it for a second, you would imagine that when you come to analyze things and prove this lemma and so forth, you're going to see a matrix and you want that matrix to be non-singular, right? That's all the time happen. Van der Monde matrices and so forth. In our case, the matrix is going to be this form. So you're going to have this C1 up to CS. These are the coefficients of the polynomial. You want to prove there are at most s minus 1 zeros. So by contradiction, you assume there are s zeros. So these are the t's and these are the c's. Okay? And what you want to show is that this determinant is non-zero. And it actually follows from the beautiful LGV lemma and so forth, but I won't get into that. And then you said, OK, you proved that this is a non-zero determinant, which makes everything work. But why won't you do like the standard computer science thing and take everything modulo p now? I mean, that's your problem, right? You have big alphabet, so do modulo p. So it doesn't work. Not probably, but you see in the computer, it doesn't work. And it shouldn't work. I mean, if it worked, there is a magic behind it, because This is not math, what I'm going to say now. But you can't have one prime, which you probably want it to be of poly n size, fighting against exponentially many tests. Right? The number of t's and c's that you're going to have, the sequences is something like that. It's n to the s. If you think of it as a kind of a typical behavior, then each of these, you want all of these matrices to be non-singular. Each of these matrices would be non-singular probability, like 1 over p, 1 minus 1 over p. So you can't have, so really what you want is something like this. That won't work unless p is very large. This is not math, okay? It's not really heuristic. But the point is that you can change the construction slightly so that now, where is the matrix? There was a matrix here. Oh, here it is. Now, for the adversary to win, you don't need one matrix to be singular, or singular. He needs to make all this polynomial to be 0. So this is a polynomial, a linearized polynomial. So I think of this polynomial as over 0, 1 to the n, 0, 1 to the s. So you can tweak the construction such that it will fail only if this is 0 as a polynomial. How to do that? Like an adversary needs to be, it's not a magic now. Now that should be okay. And the heuristics, so this is not math again. The heuristics is, okay, you still have n to the s adversaries, but now in a sense you have like s independent random variables. And the probability all of them will fail is something like p to the s. You can even say p to the 2 to the s because there are 2 to the s points, but even when you don't do math, you need to worry about correlation. So only p to the s. And now you need this to be smaller than 1, and it's when p is polynomial in n, and that should work. Okay, sorry. Actually, here it was. Sorry, yeah. P is a number, right? It's not a probability. Right? Sorry, yeah. I think of probabilities when I see them. Okay, so this conjecture is, you cannot disprove it, by the way, because we don't need it to work for s equals 3, and then you can try to be bad. We need it to work only in the asymptotics, as s is at least log n. So in order to disprove this, you really need to understand these matrices, which, if you already try to do that, try to prove the thing. Good. So if that conjecture is true, namely you can do that, then you get a constant alphabet, a number of colors tree code, not 4, but constant. And I think I'll stop here. Okay, thanks.
Questions?
So you said that evaluation codes don't seem to behave well, but now you're suggesting that you think that this evaluation code does.
That's true, David. But not provably. So, I mean, I don't know if we have, I guess everything, well, not everything works. A lot of things work, and maybe you can cast them as evaluation, but the question is, is it the thing you can analyze? I really don't know how to analyze these things. Yeah. But you're right, I'm kind of contradicting myself by using polynomials here, right?
So conjecture is that modulo p, this is it modulo p, or is this determinant?
Yeah, sorry. That's fine by itself. Every point is okay. Over in the field fp or f, whatever. So you just want this thing. You want the Boolean cube to be kind of pseudo-random for these matrices, because the general position 2 to the s points will not make this 0. So you really want the Boolean cube to be unrelated to that. We actually proved it to some extent in some cases, but
But you're thinking of this as a matrix with variables indeterminates x, not over the hypercube.
But I think of this as, so this is the polynomial, but I only evaluate it when xi are plus minus or 0, 1. So by the way,
Any one of the evaluations to be non-zero.
You will win if one of them is non-zero. Yeah, anyone, that's the same thing? Yeah, okay, good. Yeah.
But that's equivalent to showing that this is non-zero as a polynomial in x1 to xs.
Yeah, exactly. The same thing. Well, you need to linearize it, but you can.
So the x square equals x, that's what you, that's what you get.
Yeah, but actually there is a nice little trick. You can actually write it explicitly like that.
Oh.
Because right, when xi is 0, it's okay. When xi is 1 is the Pascal. So you actually have you have your hands on it, and we proved that under some mild conditions that is the case. In fact, it's a pseudo-random on the Boolean cube, but it's not a proof for which I know. Thank you.